Hello everyone, my name is Shijie Li. Today is really excited to present our work, Global Aware Monocular Semantic Scene Completion with State Space Model. This work is collaborated with Zhong Yaocheng, Rong Li, Shuai Li, Yougen Gao, Xun Xu, and Xulei Yang. In this task, we aim to reconstruct a complete 3D semantic occupancy map from just a single image. This is called Monocular Semantic Scene Completion. It's useful for many downstream applications, such as robotics, AR, and autonomous driving. Previously, solutions like MonoScene mainly use CNN-based encoders and decoders, but CNN are limited by their local repetitive field. This makes it hard to model the global context, which is important for handling perspective projection and depth ambiguity. To improve this, we need global modeling in both 2D and 3D domains. In 2D, we can use transformers, which capture spatial relationships well. In this way, we can also utilize many pre-trained visual foundation models. In 3D, however, transformers are too expensive. Thus, we use Mamba as state space model, which models long-range distance efficiently with linear complexity. We also found that directly arranging voxels by their 3D coordinates introduce disconnectives. So we propose to reorder them in fast-term space for smoother sequential consistency. Our contributions are threefold. First, we design a hybrid framework, GA Mono SSC, that integrates transformers and Mamba to achieve global awareness in both 2D and 3D. Second, we propose a dual-head multimodality encoder that extracts the semantic and geometric features separately and models spatial relationships across 2D features. Third, we introduce a fast-term Mamba decoder with a fast-term reordering strategy to capture long-range dependency in 3D space while reducing feature disconnectives. Our encoder is designed to be lightweight while still powerful. It takes the input image, split it into patches, and then processes them through transformer encoder blocks. This allows us to capture global context in 2D, which is especially helpful to reduce the imbalance caused by perspective projection, where distance objects appear much smaller than closer ones. At the same time, we extract multi-scale features separately for geometry and semantic. This separation helps the network focus on structural clues like room layout or object boundaries, which also learns high-level semantic information such as object categories. Together, these features provide a strong and compact scene representation that supports downstream 3D reasoning. In the decoder stage, we fuse the extracted features into a 3D voxel space and then apply what we call fast-term Mamba decoder. The key idea is that directly modeling voxels in the original 3D space often leads to disconnective and inconsistent ordering, which makes the sequential modeling very difficult. To address this, we introduce fast-term reordering. Instead of keeping voxels in arbitrary 3D positions, we rearrange them into a sequence along the fast-term space. This reordering ensures that neighborhooding voxels, which are naturally related from the camera's perspectives, are placed closer in the sequence. By doing so, the input to the Mamba layer becomes much more smoother and more consistent, which greatly facilitates sequential modeling. On two widely used datasets, NYU-V2 and OCC-SkyNet, our method achieves state-of-the-art results. Compared to strong baseline ISO, we improve mean IOU by about 1 point on NYU-V2 and about 7 points on OCC-SkyNet. This shows the advantage of combining transformer and Mamba architecture for global modeling. Here, we show some qualitative comparisons. Our method produces more accurate 3D reconstruction and fewer errors in semantic prediction. This demonstrates that GA Mono SSC is better at recovering fine structure details. Thank you for your watching. The code is already available.